Why does a simple greedy search consistently outperform eigen-decomposition and iterative optimization in clustering? A recent theoretical framework finally explains why. Traditional clustering treats clusters as sets of similar points. That paradigm collapses on irregular shapes, varying densities, or multi-scale structures. Even spectral and deep clustering methods hit fundamental limits because their assumed geometry rarely matches the actual data-generating distribution. Cluster as distribution, or KD, solves this by treating each cluster as independent samples drawn from an unknown underlying distribution. It represents these distributions using kernel mean embeddings in a reproducing kernel Hilbert space, then assigns every point to the most similar distribution proxy via a single greedy pass. But why does this work so well? The theory decomposes the approximation error between the true distribution and its empirical proxy into three precise components. First, truncation bias, which measures how well the high-density region captures the full distribution. Second, estimation bias, which converges at an O of 1 over square root of S rate as you sample more points from that dense region. Third, core bias, which depends entirely on how representative your initial core clusters are. Here's the critical insight. Once those core embeddings are fixed, the one-pass assignment isn't heuristic. The objective decomposes additively across points, and the constraint that each point belongs to exactly one cluster forms a partition matroid. By the Rado-Edmonds theorem, greedy selection on a matroid is globally optimal for linear objectives. The greedy pass isn't approximating optimality, it's achieving it. Combined, this yields a near-optimality guarantee for the full clustering objective, with regret tightly controlled by those three error terms. It also proves exact label recovery whenever the embedding error falls below half the distribution score margin. Empirical validation confirms the bounds hold, and shows KD consistently outperforms kernel k-means and spectral methods on non-convex, density-heterogeneous data. If you're working with complex cluster structures, this distributional perspective fundamentally changes how you should approach assignment. The full proofs and experimental breakdown are available in the paper.